All right, welcome back. So this is the second half of the Unit D, Chapter 1 review. Okay, I left lesson 1.4 because it's a little longer than the other one, so I split this into two parts. So this lesson is all about nuclear reactions. So first you need to understand is the difference in magnitudes of order of energy that is produced by nuclear, chemical, and phase changes. Okay, so phase change, that's this. This is just basically going from a liquid to a solid, or a solid to liquid, or in this case, gas to liquid for water. And you release a certain amount of energy for sure. Like we put the ice cubes in the freezer, or that's, yeah. So you need to, you get some energy, not a ton. As soon as you start burning things, you have a chemical reaction, and you get definitely like a magnitude. You can see about 10 times as much energy are involved in the combustion reaction. But then you take a look at the nuclear reaction, and holy cow, you're talking about like times like a million or a billion times more energy, actually, while you were at 100. So let's say a million times more energy when we're talking about nuclear reactions more than chemical reactions. So really high amounts of energy is the idea that you should be getting. Okay. So nuclear reactions, this is why we want to use these and why we're interested about them. It's because they release so much energy, and we want to capture that and make our electricity with it. So before we start really digging into nuclear reactions, we need to understand the type of radiation that can be produced with radioactive decay. And we have three types of radiation that you need to understand and use. We got alpha. There's your little symbol for it. It basically looks like helium. Well, it is helium, and it's not very penetrating. It's actually quite neutral. So then we have beta radiation, and this is a high-speed electron moving very quickly. It's more penetrating, so it can go a little bit deeper. And then gamma radiation. This is very penetrating. It does not have mass, as you'll see from its symbol here. It's got no protons or neutrons or electrons, so it does not have mass, right? It's this electromagnetic radiation. This is EMR that we studied in the last unit. This is the stuff that can go right through you. Alrighty. So, you do need to understand, you can describe a nuclear reaction using pictures or through actual equations, which is what we're going to take a look at next here. Oh, after this one. Okay, so first off, an example of a diploma question here where we need to use the numbers above to choose one type of radiation and match it with the number of characteristics of that radiation and with the number of the nuclear reaction of that that's producing that type of radiation. Okay, so there's three different possible choices here. So let's take a look. So type of radiation, we've got alpha. Remember, alpha particles are helium particles. So there it is. I see helium being produced in number 8. So we got 1, something, and then 8. And so these are negatively charged, I don't know. Photons with no mass or charge? No, these are helium. They have a mass. Positively charged molecules. Yeah, well, they're going to be positive. They're not negative. So, okay, we'll take 6. It's not ideal, but we'll go with it. A beta particle. What's a beta particle? It's the same thing as an electron. Okay, so they're negatively charged. So 2, and then 4, and then 9 would be another correct answer. And then lastly, gamma. These are photons with no mass or charge. 5, and there's your gamma ray in a reaction. All right, so those are your 3 possible answers that you could have chosen for that question. Again, I want you to pause. I want you to see how much you remember from balancing nuclear reactions to see if you can figure out what number A and B are here and C and D. So pause and go ahead. All right, so the key thing you need to remember when you're dealing with nuclear reactions is that all your mass numbers on one side of the arrow have to add up all the mass numbers on the other side. So on our reactant side, we have 240, so 39 plus 1 gives us 40 mass numbers. Sorry, pause there for a second. So these numbers here have to all add up to 240. So watch out for this. This is something we might not have caught before. This 3, you need to multiply each of these numbers by 3. So there's no protons on the bottom, but 3 times the one on the top here. So we have a 3 for the mass number there, and then we don't know C and D, and we don't know, and then we have 147. So let's figure out. So 147 plus 3 gives us 150 plus whatever our unknown is to get us to 240. So if we add 90, 150 plus 90 will get us to 240. So CD must be 90. All right, then we need to look at our atomic number and try and figure out the atomic number for beryllium. We have 94 on the bottom and 0. So this side is total is 94. So we need this side to add up to 94 as well. So right now we have the unknown AB, and we have 38, and we have 0 here. Even if it's 3 times 0, it's still 0. So 38. So we'll take 94 minus 38. And 56. So if we add 56 plus 38, we'll get 94. So AB must be 56, and CD must be, what was it, 90. Alrighty, this is a chart I added to this lesson. I wish I had seen it before in the last lesson, but I really like it. It compares fission and fusion. Okay, so first off, fusion is what's happening in the sun, right? So we're joining two atoms into one larger one. So this is happening in our sun with hydrogen, and those two hydrogens, so these are both hydrogens, they become helium. Okay, so your product is helium. So we can't harness this yet. We're working on it a lot because we would like to. We can't harness the energy from this yet to create electricity, but really working on it because we want to work on this because the byproduct of helium is an awesome byproduct, much better than some other byproducts out there, and the amount of energy you get from using hydrogen is 3 to 4 times more energy than from fission, which is a lot of energy to begin with too. So fission is the one. This is used in CANDU reactors. CANDU reactors. All right, so all of our nuclear reactors use fission, all of them. Okay, and this is where you're taking a larger atom and you're splitting it into smaller ones. Now you might need to use like a neutron to hit that, to start the reaction, to hit that larger atom, to start the reaction. But each of these new substances will also form a nitrogen. Oh, here it is over here. So we have a neutron to help get the reaction started. The energy is released when these smaller products are formed, but as they are formed, more neutrons are formed. This is also why you hear the term chain reaction. You can see from one neutron, you've now got 3 neutrons being produced. Each one of those neutrons can then go do fission again and start the next reaction. So it's called a chain reaction because it keeps getting more and more. All right, and the reactants in fission are uranium and plutonium. The byproducts are nuclear waste and it is radioactive. So this is one of the issues with nuclear reactions, nuclear energy. It can be used to produce energy and electricity, and this is what we use in these fission reactions for. And they're a million times more energy than any other energy source that we are using. Right, CANDU reactors, or any kind of nuclear reactor, is very similar. So we have an internuclear potential energy that is in that uranium or plutonium. All right, so in here we have our this is our containment structure. This is where our reaction is happening in the reactor. This is where the heat is being released. The heat is being, you can see the heat is pumped and coming back here. So it's not actually, the steam is not touching the reactor, but that it is going up through the steam line, and then the steam is turning the turbine. Okay, so from this point, it's exactly the same as the reaction in a coal-fired plant, right? So you've got the steam, actually from here, the thermal energy, heating the steam, turning it into kinetic energy by turning the turbine, which turns the generator and creates the electrical energy. So same pattern here, right? It's just that first step where the energy source is. That's different. All right. This is just comparing and contrasting the coal-fired plant with a nuclear power plant, and you can see both energy sources are considered non-renewable. Okay. The form of energy in the source. So coal contains chemical potential energy that has been stored from the solar energy, and then uranium has the intranuclear potential within its nucleus. Combustion is the actual reaction that's used in a coal-fired plant, whereas nuclear fission is what's used in a nuclear power plant. Did I say that again? Okay. Energy conversions that are happening here. So this, you have from the sun to the plant, which stores it as chemical potential energy, into the coal over time. It's burned and it's stored as chemical potential energy. That shouldn't be an arrow there. And then it's burnt, so you get thermal energy, so it's combustion, and that turns the turbine, that turns the generator, that creates the electricity. Nuclear power plant, we have that internuclear energy that's in the actual nucleus of the uranium. You start a fission reaction and you get the heat, the thermal reaction, which again turns to kinetic as it turns the turbine, and then electric as it turns the generator. So you can see the last three energy conversions are the same for both of these. Benefits and costs of nuclear energy. Benefits, it produces large amounts of energy compared to burning coal. So it's very efficient. Disadvantages, nuclear materials can be used in nuclear weapons. Nuclear material is radioactive. Benefits. There's no real carbon dioxide, sulfur dioxide, or particulates, so no gaseous emissions. So that's a good positive benefit. Its disadvantage is a non-renewable fuel source, so that fuel source again won't be there forever. Thermal potential, so it does release a lot of heat into the air and water. You need these big cooling pools, so you're doing a lot of thermal pollution, which has its other own issues. You'd be heating bodies of water and stuff, and then there's the issue of storing the radioactive waste, and then always the risk of a meltdown. Economics, it lower operating costs. Unfortunately, they're really expensive to build these plants, and that's one of the reasons we're not seeing a lot built currently. But we do have a lot of uranium, so that is a benefit. Example diploma questions in about this initial section of the lesson. Is each of these nuclear processes fission or fusion? Can you recognize them? Okay. I always think of fuse. This is how I remember it. Fuse is you're fusing something together, you're burning something together. So if you see two nuclei or two elements turning into one element, to me that's, well, not to me, to everything, that's fusion. Okay. Now this is where it might get tricky, and I want to really point this one out. This neutron, you can see it here as a reactant, but over here you can also see it shows up as a product plus 5 of them. So that means this neutron wasn't really used up in the reaction. So this is just used to get the reaction started. So we don't consider this being fused. It's not fusing in there. So this is just getting the reaction started. So this is fission. because you have this big plutonium atom and it's being split into two smaller elements. All right, here's one atom into two smaller. Again, this is going to be fission. And this is one atom into two smaller, so this again is fission. So there's only one example of fusion here. Example diploma question. One of the main reasons that many countries use nuclear power plants is because they are, okay, these are true, they're not inexpensive to build. That is not a reason that many countries use them. They do have a high energy put out. Do not create thermal pollution. That's not true. Create large number of jobs. In the construction of a nuclear power plant would have a lot of jobs, but once it's built, I wouldn't imagine there's a lot of jobs. Not like this is a really good question. I'm gonna have to go back and double check that one. I'm guessing it's the main reason that countries use nuclear power plants is because they have the high energy output. I'm just not sure about the number of jobs they create. That's interesting, but that wouldn't be the reason that they would use the energy source anyway. It's because they have such a high energy output. All right, the chain reaction that occurs in the CANDU nuclear fission reactor. So you see you have that neutron hitting the uranium, getting two smaller elements or atoms, and we still have the neutrons being released as well, 3 times as many. So 1 neutron goes in, 3 neutrons come out. 3 neutrons go in, how many neutrons should be coming out? Well, it's 1 to 3 ratio. So if it's 3 here, then this should be 9. So for every reaction of uranium, you should also get these 2 plus 3 neutrons. So there's another reaction. 1, 2, 3 neutrons. Another reaction of uranium. 1, 2, 3 neutrons. So we should get 9. This is the chain reaction concept. Now you have those 9. Now they're going to go hit, these 9 neutrons are going to go hit 9 uraniums. All right, E equals mc squared. We got to use Einstein's formula in this lesson, which is very cool to say that you've used this. Remember that this is a way to figure out how much energy is released in a nuclear reaction, because in a nuclear reaction, you're looking at the mass change between the reactants and the products, and that mass change is converted into energy. All we have to do is find the change in mass and multiply it by the speed of light squared. All right, so steps, here's an example diploma question. Steps used to calculate the change in energy for a nuclear reaction. Okay, so what are the steps? So you gotta list them in order. So we have balance the nuclear reaction equation, calculate total energy released, multiply the mass of each nuclide by the number of moles in the equation, determine the mass change by subtracting the mass of the reactants from the mass of the products. So, first thing you always have to have is a balanced nuclear reaction. So 1 is going to be our first. Okay. Last, calculate the total energy release. That's going to be our last. So let's put it there. And then which one of these comes first? Well, we need to multiply the mass of each nucleide, which is like each substance in our reaction, by the number of moles in the equation. So that's going to be the second step. And then determine the mass change by subtracting the mass of the reactants from the mass of the products. That's our third step. And then lastly, we're going to use Einstein's formula. So a lot of things we need first. We need that balanced reaction. We need to subtract the masses of the reactants from the products. And then we can use Einstein's. Okay, so here's when we can actually do the calculation. You want to pause this and then read through it yourself and see if you can figure out what you actually need to do for this question. Then come back and check. So natural gas is often found trapped in layers of shale that contain large amounts of radioactive potassium. As the potassium isotopes decay, they emit gamma radiation. All right. When drilling to find natural gas reserves, geologists may look for high levels of gamma radiation from rock layers. So gamma radiation, so gamma decay of potassium-40 and associated nuclide masses. So we have the potassium isotope decay. There's our potassium. And it is decaying into argon, an electron, which is our beta decay, and we also get a gamma radiation. Gamma has no mass, and it's giving us the mass of an electron. It gives us the mass of argon and krypton. So we don't even need to go to our data booklet, which is awesome. So now it's asking us the change in mass that occurs during this radioactive decay for 1 mole of potassium, that's what it's balanced for, is expressed as this. Okay, so we need to find the change in mass that's happening here. And the change in mass is going to be equal to the mass of these reactants, all added up, minus the mass of the products. Okay. Or the other way around. Doesn't matter, you just need to find the difference between these two sides' masses. So you can see the reactants mass is here, and then we just need to add up all of these masses of our products and then see what the difference is between the two sides of the reaction. All right, so I've added these two together, 39.3, no, 0.9629321 plus 0. So we need to now find the difference between these two numbers. All right, and the difference is always going to be positive because you're trying to find how much mass is the differences between the reactants and the products, and this is how much mass it has been changed in the reaction. And our units are in kilograms, and it's times 10 to the negative 3 as well, right? This number. However, they're telling us it's already in 10 to the negative 6. So this number times 10 to the negative 3 is the actual number. So I'm going to move this down by 1, 2, 3. So I'm going to be 1, 2, 3. Then 1, 2, 1, 0, 6, 7, 9. And then this will give us the time. Then that makes much more sense. Times 10 to the negative 6. So the numbers that we're basically looking for are the 1, 0, and the 6, but we're going to round up the 6 to a 7. So the answer should be 1, 0, 7. All right, I'm not going to go over these ones because these solutions were from the lesson. So there is a video for each of these if you want to do some more practice with Einstein's formula and figuring out the amount of energy is released when the mass changes. So that is the end of this part B. Make sure you connect with me if you have any questions.